Hey scholars, this is Mrs. Gregerson. We're working on similarity in right triangles. Today we're going to do stuff that kind of can seem hard at first, but once we get going with it, it works pretty easy, but you have to understand similarity very well. So we're going to review on how to prove triangles similar. We had three different ways. We had angle-angle similarity, where you showed two pairs of congruent angles. We had side-angle-side similarity and side-side-side similarity. So those were the ways that we had. Now, the first thing we're going to do is we're going to start with these. A lot of these theorems are going to seem very confusing at first, especially with the wording. But once we get going, it's not too bad. So just kind of bear with me on the wording of things today. It will get better. But it also means practice and having your notes really close to you while you're doing the homework. Alright, this one says the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. The original triangle they're talking about is this big triangle. And they're drawing the altitude right here to the hypotenuse of the larger triangle. Well, obviously you form two smaller right triangles. So we're going to use angles maybe to help us figure this out. And so we're going to redraw and figure out how they are all similar. So let's do it this way. What if I let this angle be 65 degrees? I know on the larger triangle, ACB, because right triangles, the acute angles are complementary, I knew this would be 25 degrees, which makes this one 65 and this one 25. Now, how did I do that? I used the fact that acute angles of right triangles are complementary. Now let's redraw them. Let's draw the larger triangle first. I'm going to draw that in blue. So we have ACB right there. So A, C, B. So we got 65 and 25 right there. Okay, then I'm going to redraw ACD. That's going to be the small one here on the left. And this is 25 degrees. This would be 65. And notice I'm just redrawing them. And then we're going to do our other one, we're going to do that one in black. It's just a little bit larger one, the middle-sized one, if you want to think about it like that. Alright, and this is going to be C, D, B, but we're going to put our angle measures in there. There's 65, there's 25, and I don't like how that's not writing well. Let's see if I can find another one that will do any better. Let's see, don't know if that will work or not. 25, yeah, a little bit better, and 65. Okay, now I want to write a similarity statement. Now, remember, a similarity statement is stating two figures are similar. So I'm going to start with the very top one. Okay, we're just going to go triangle ABC. All right, ABC is going 65, 25 to 90. So that's how we're going to have to match it. I always want to use the corresponding angles because it's easier to think sides. So if I go 60 to 25 to 90, I'm going to go to the smaller one here. I'm going to go A, C, D. Then if I go 65 to 25 to 90, right, we're going to go C, B, D. Now, no matter which pair I pick, I know those triangles are going to be similar, and it's all because of AA similarity. So we know that's going to work. Now, we're going to be able to set up a whole bunch of proportions based off of this, but we have to get a little bit of vocab in there too. We have what's called a geometric mean. Now, a geometric mean is the following. Now, here's the definition of it. The geometric mean of two numbers, A and B are two numbers, okay, is the positive number such that, notice the proportion I have here, A is to X as X is to B, that therefore X is the square root of AB. Basically what they're doing is, geometric mean is, I don't know what my means are in that proportion and I plug it in. It is not an average. Mean normally means average, but geometric mean means I'm looking for a missing connector. Basically, I'm looking for those two parts in the middle. And they also say it's a positive number. So notice there's a square root there, but there's not a plus and minus out front because it has to be positive. And here's how easy it is to find the geometric mean of two numbers. You basically just go like this. 32 is to X as X is to 8. You put in the means, X, the same variable, and then you just cross multiply. So I got X times X equals 8 times 32, so X squared is equal to 256. Then I just take the square root of it. And again, because it's a geometric mean, I don't have to worry about the plus or minus. So x is going to be 16. So the geometric mean between 32 and 8 is 16. Let's try another one. Here we want the geometric mean between 4 and 16. So do the same thing. These go in the extreme spots. Go in extremes, okay? So we get 4 is to x as x is to 16. So we get x times x equals 4 times 16. And remember, x times x is x squared, not 2x. So I get x squared is equal to 64. I'll take the square root of that. X is going to equal to 8. Now, sometimes it's not as pretty as that. Sometimes they're not as easy to do. Maybe there's fractions or whatever. That's okay. But to set up to find the geometric mean, it's always that easy. Like here on C, 11 is to x as x is to 7. When I say anything about geometric means, think proportion, and it's that number that's the same in both the means location. So when I do that, I'm going to go x times x equals 11 times 7. So I get x squared equals 77. I take the square root of both sides, plus or minus, but I drop the minus because geometric mean is always positive. It'd just be the square root of 77. And so that's okay. So that's how you find a geometric mean. So we're going to use the fact today, these two things, that I can get 3 similar triangles out of this diagram, okay? And I'm going to use geometric means to find the missing side lengths using similarity. All right, we're going to go to the next page, and we're just going to start practicing.